Hi and welcome to Profex Tutorials. In this episode we are going to do our first Rietveld Refinement. We will continue processing the dataset of the previous episode, so if you haven't seen it yet, you may want to check it out first. In the previous episode we used the search match module to identify the phase content in the raw data file. We found two phases, beta-TCP and hydroxyapatite, and pinned both in the search match module. No other phases seem to be present. So now that we know which phases occur in our sample, we want to create a refinement project, and we can easily do this by clicking the Add Remove Phase button. This will show the Add Remove Phase dialog, and because we pinned some phases, they are already pre-selected, the apatite and the TCP beta phase. We could also just add a search manually if we, for example, if we want to add this pyrophosphate phase, we just filter and select the CPP phase, but we know that this is not present. Also because we selected the RMSD8 instrument for the search match process, it already uses this information here, so it pre-selects the same instrument, the RMSD8. If we don't run a search match first, we have to make sure that here we select the correct instrument configuration. So again, we have to select one of these many bundled configurations, and it will remember our previous choice. So once we select our own instrument, it will always suggest or pre-select this instrument, so we are not bothered by these many configurations from other institutions and universities. So the first time we create a refinement project, this box will be checked automatically. It means that it will create a default control file because we don't have a refinement control file, and we'll see in a minute what this file is used for. So this has to be checked, the right instrument has to be selected, and the phases we know that occur in the sample have to be checked. Then we click OK, and now we will get a new text file here. This is the refinement control file. We don't need the search match module anymore, so I will close this. And this is where we define which phases on which instrument we want to refine. So it looks a bit like programming code, but it's actually quite easy to understand, and there's a lot of comments. Any line starting with the percentage sign is a comment, so it's ignored by the program. It's just for our convenience. And it starts with a sample ID. That's the ID shown here that we programmed when we entered when we programmed the data collection at the instrument. And then it says the next variable is the theoretical instrument function. So that's the instrument configuration file we selected, the RMSD8 instrument. Then at some point we had to select the wavelength file, the file that describes the spectrum of the characteristic radiation used by this instrument. We selected in the search match module, and we used the copper radiation file. And then it lists two structure files, structure 1 and 2, the ones we added in the search, in the add remove phase dialog, apatite, hydroxyapatite and beta-TCP. And then it automatically added some information, a measured background file. This is coming from the instrument configuration, so it already knows it has a measured background stored in the template. And the scan file is listed here. And then two important lines, the minimum angle and the maximum angle. So in the raw file, I said that there is no useful data between 4 and 10 degrees. So by default, this is already setting the minimum angle to 10 degrees. So it means it will be ignoring all raw data below 10 degrees. We could also clip the upper end. For example, if there was no useful data above 55 degrees, we could set the maximum angle to 55 and ignore this part. But there is data, so we will just leave this commented, so inactive. And the next few lines are file names for output files. They were entered automatically when we created the control file. And then it lists a few refined parameters for the 0-point displacement, sample height error, and sample transparency. So usually this was all entered automatically when we created the default control file, and for the first simple refinement, we don't have to change any of this. At the bottom, this part of code is where the relative phase quantities are calculated. So all this was generated automatically by using this add remove phase dialog. And to run the refinement, we can immediately start it. This is all we need for now. We can just click the button Run Refinement and perform the first Rietveld refinement. So it's pretty quick. And the difference curve usually is the first thing I'm looking at. Is there any major differences between the refined and the measured data? There are some differences we have to fix, but in general, all the peaks are assigned. The profile fit doesn't look too bad. The shape of the peaks is quite okay. So, but there is some work to do to improve the refinement here. So now we see some refinement output here. The refinement statistics, the weighted R profile factor, the expected R profile factor, chi-square, and the goodness of fit, which is basically chi, so the square root of chi-square. It used 10 background coefficients for the Chebyshev polynomial background. And what we are usually interested in the most is the quantities, the phase quantities. So it's normalized to 1, not to 100. So we have 20% hydroxyapatite and 80.00% beta TCP. It also lists some structural parameters, the refined the chemical composition here, and the A and C cell parameters multiple times for some reason. So on the left-hand side, we see the output of BGMN, a lot of cryptic numbers. This is only important if the refinement fails. So if we get an error message, we should have a look at the output of BGMN, because that's where we probably can figure out what went wrong and how to fix it. The graph shown here, the convergence progress, is showing the two R values, the weighted profile R and the expected R, and the chi-square, the ratio of the two. If we click with the left mouse button, it will zoom in by a predetermined factor. If we click again, it will zoom out to 100% again. So it's just helpful to see what's going on here, because usually this value starts at 100 and it goes down very quickly. And we are mostly interested in this area here to see how close it gets to a chi-square value of 1.5. So we zoom in. If we use the right mouse button, we can also hide the legend. So now we can see what's going on. The chi-square value of 1, let's show the legend again, is if RWP and Rx are the same value. So this one, the RWP is a bit higher, so chi-square is a bit higher than 1. In fact, it's 1.86. And as a rule of thumb, we the chi-square should go below 1.5. And the two blue lines are basically what we are striving for. So the dark blue line down here is a chi-square of 1, and the light blue line is 1.5. So if the red line goes below this line, reaches the blue background, the area between these two lines, we are on the right track. So the refinement is converging well. So here we are still a bit above this range, and we can also see in the difference curve there are still quite some differences, some room for improvement. And hopefully if we fix this, if we improve the refinement strategy to better match these areas here and here, then we should be able to reach this blue range down here with the red line. So this is just a visual aid to see how quickly the refinement improves while it is running, and at the end, if we are somewhere in an acceptable range with a chi-square below 1.5. So next we have to decide how do we want to improve this refinement, and we have to analyze where these differences come from. If we zoom in, here it basically just looks like a slight intensity mismatch. Also here we have to keep an eye on this. If there is another phase hidden here, maybe we will see it if the refinement gets better. And for the strong peaks here, it's pretty close, but we have overestimated this intensity, and this one underestimated here. There's a little problem with the feet, with the width of the peak. So, but it definitely looks like the blue phase is beta TCP. We can just highlight it here by clicking on beta TCP. The green one is hydroxyapatite. The green one looks very good. So of course the signal strength is weaker, so if there is a mismatch, we wouldn't see it as easily, but it looks very good. So the problems we see, they all come from the beta TCP structure. So we have to fix something in the refinement strategy of the beta TCP structure, and as we can see in our refinement control file, the structure is defined in the file tcp-beta.str. So we have to edit this file, and we can easily open it by right-click on this line and select Open File as Text. So now the tcp-beta.str file opened, and we will see the structure description of the beta TCP crystal structure. And this is a file format that is proprietary to BGMN. It basically has the same content as the standardized CIF format that is used to download structure files from some databases, for example, and for publications. But it is a different format, and we have to convert CIF files to this STR or structure file format used by BGMN. But it is relatively easy to understand. The double slash sign is used for comments. So what's written behind the first double slash is ignored by the program, and I usually add the database code. So this is a file from the PDF4 database. So just to have a reference to the database record somewhere in this file. But here the phase keyword is just the name of this phase. We can also add a mineral name. The formula is not used for the refinement, it's just for information. And then we have to specify the space group number from the international tables and the Hermann Mogin symbol in the full notation, also from the international tables of crystallography. So this is a hexagonal space group. number 161 in the rhombohedral space group R3C. On the next line, we see the unit cell parameters A and C, and I will come back to this in a minute. So basically we see the A value always given in nanometers, not in angstrom. So it's 1.04 nanometers, that would be 10 angstrom, and C is 3.7 nanometers, that would be 37 angstrom. The next line is rather cryptic, but very important. I will skip it for now. I will come back to it in a minute. Let's just first have a look at the rest. The goal statement just instructs BGMN to print something to the output file, to the results file. So here we instruct BGMN to list the grain size in the crystallographic direction 111 in the refinement results file. And this parameter beta TCP is used to calculate the phase quantity. It's basically related to the scale factor, and we will also come back to this later when we see what this Gewicht parameter that is refined here actually means. And then we have a list of atoms, atomic positions, starting with E for element, and then the element symbol. This is calcium. We can also use ionic scattering factors, but we have to write it like this. So if we want to use the calcium 2+ scattering factor instead of the neutral calcium one, we would write it like this. And the same for the oxygen. For the 2-, we have to write -2. And it would just be using the ionic scattering factor instead of the atomic one. Unfortunately, BGMN doesn't know the ionic scattering factor of phosphorus 5+, which is the oxidation state in the PO4 tetrahedra. So we cannot use this. We will get an error message. We can only use the neutral one for phosphorus. And since we should not mix ionic and neutral scattering factors in a structure file, we have to use the atomic ones here, because we cannot use ionic ones for all elements because the one for P is missing. So that's just a side note. Usually we don't change this anyway. The next keyword is the Wyckoff symmetry description. It's also just given by the crystal structure. And then we have fractional coordinates x, y, z, and the thermal displacement parameter given in nanometers squared. So the numbers are 100 times lower than what you usually see for the B factors given in angstrom squared, but just because it's nanometers squared, so it's smaller by a factor 100. So to come back to this important line here, it's basically the line we edit the most often. And now the context help comes in very handy, so we can open the context help window. And if we want to know what this RP variable means, we can just place the cursor here and press the F1 key on the keyboard. And it will show us the description from the BGMN help file, what RP means and what values we can enter here. It's still a bit cryptic, so usually we leave it at RP4. Basically, it means we can refine crystallite size peak broadening and microstrain peak broadening. If we would change it to RP3, we could only refine crystallite size peak broadening, but no microstrain. And in case of RP2, we would not refine any peak broadening at all. So usually leaving it at RP of 4 is the safest solution. We can still control how, if and how we refine the two peak broadening parameters, crystallite size and microstrain. Then let's go to the B1 parameter. Show the online help, the context help, by pressing F1, the F1 key, function 1. And it says that this is crystallite size caused line broadening. So by refining B1, we can refine peak broadening that is originating from small crystals. For K2, it says it defines the square of the microstrain. So by refining K2, we can refine the peak broadening originating from microstrain. And K1 is crystallite size distribution. So if we have a wide size distribution of nanocrystals, it would change the shape of the peaks a little bit, because some crystals broaden the peak more than other crystals. So we can fix it or refine it. Now, how do we refine something actually? So the example K2, the microstrain factor for peak broadening, it says K2 is 0. And if we leave it like that, it will stay at 0. So it's fixed, it's not refined. So in this first example, we did not refine peak broadening originating from microstrain. Instead, we just kept it at 0. But if we right-click with the mouse, we can select refine isotropically, refine anisotropically, or fix the parameter. So if we want to refine peak broadening from microstrain, we start with isotropically, which is a bit easier. Less variables introduced in the refinement. So we click on this, and now we can see how this parameter changed. It added the keyword param equals as a prefix to K2, and behind the value 0, it added an underscore 0 and carré positive value. So what this means, by adding param equals as a prefix, we release the parameter for refinement. And the starting value is 0, but it's now variable. It will be fitted to the measured peak width. But to limit the variability of this parameter, we can provide a lower limit following the underscore and an upper limit following the carré symbol. So now K2 is refined. It starts with a value of 0, and it can vary between 0 and 0.0001. And as we can see here from the B1 value, B1, let's show the context help again, is the crystallite size caused line broadening. This was already refined, starting with 0, ranging between 0 and 0.001. So if we use the right mouse button again, we can fix it, and now it is changed to B1 to a fixed value of 0, and we can release it again isotropically. So now it can vary again. We can also set it to anisotropic refinement, so it can use different values depending on the crystallographic direction of the lattice plane. This is helpful for crystal morphologies that are strongly anisotropic, for example needles or platelets or whiskers. The one value for the crystallite size is not sufficient, because a needle has vastly different needle length than diameter. So depending on the crystallographic direction, we should use a different crystal size for the length of the needle and for the diameter of the needle. That would be an anisotropic refinement. And in fact, hydroxyapatite sometimes, if it's a precipitated phase at synthesized at low temperature, then it is strongly anisotropic. In a sintered high temperature sample, not anymore. But maybe in hydroxyapatite, it would make sense to use anisotropic refinement. But in beta TCP, which is a phase that usually forms above 1000 degrees, the crystals are usually fairly compact and idiomorphic. So in this phase, it doesn't make much sense to refine this anisotropically. Now the last parameter of this line, Gewicht, which is the German term for weight, it's the scale factor of this phase. But it's not exactly the Rietveld scale factor, it's already corrected for the unit cell density. So maybe you can read this, it's explained fairly well in the context help, but this is where, so in the parameter Gewicht contains the information about the phase quantity. And it's refined with a funny keyword. If we would have a simple refinement, so we can use a fixed number here, and if we would fix it at 0, the phase would just be scaled down to 0 and not be refined. We can also use the keyword param, and we can add limits, but the upper limit is maybe I just don't add it. We don't have to use limits, it's just to stabilize the refinement, but we cannot accept negative values, so Gewicht can only be 0 or positive. Now it would be refined. However, with the Gewicht parameter, we also refine preferred orientation or texture. So if we set it to a single value, even if it's refined, we would assume that the sample is completely untextured. But if we want to refine texture, we have to select a spherical harmonics function, and we can select the order of this function. And if we choose refine anisotropically, it will change to this keyword spherical harmonics of the second order. So this is still a relatively simple function. It allows one direction of preferred orientation. It might work for maybe for very strongly orienting samples like clay minerals or gypsum or anything with platelets. But sometimes this is not enough to describe the orientation pattern at the surface of the sample. So we need a higher polynomial or spherical harmonics function. If we change it to anisotropic, we can increase it to a spherical harmonics of the fourth order, which allows a more complex preferred orientation pattern. If we click again, it goes to the 6th, 8th, and 10th order, and now we cannot go any further. So 10th is the maximum. And this allows extremely complex preferred orientation patterns. And it's actually not very useful in most cases. It also introduces a huge number of variables to be refined, especially in a triclinic structure. So the refinement gets unstable and very slow. So this is usually leads to over refinement. So we try to squeeze out too much information from the data. However, if we go back to, I think that we used SPR of the fourth order in the previous refinement, which is a fairly low complexity. Actually, we can check it in the results file. This is the results from our previous refinement. And in beta TCP, yes, we used SPR4. So we can increase the model for preferred orientation here. by setting it to 6 or maybe even 8 if it's really necessary, but probably 6 will already help quite a bit. So now this is the content of a typical structure file, and now we have to go back to our refined pattern and decide what do we actually want to change in our refinement strategy. So we had some intensity mismatches here and here in the beta TCP structure. So now we have to know which crystallographic parameter changes the intensity of the peaks in the measured diffraction pattern. So we have to go back and forth between direct space of the crystal structure and reciprocal space of the diffraction pattern. We have to know the link between crystallographic parameters and features in the diffraction pattern we measured. And intensity is usually related to either the atomic positions, so for example the scattering factor and the coordinates, but also to texture. It could just be a matter of preferred orientation, what we observe. And this is usually the first thing I try. If I see intensity mismatches, I check if texture was refined, and if it was refined with a low degree of spherical harmonics, I try to increase it, repeat the refinement, and check if my fit improves. We also had some issues with the feet of the shape of the feet here, of the strongest peak here and here. So it's somehow related to peak width. And for peak width, we have the two parameters, B1 for crystallite size, but this one was already refined before, so we just leave it. And the K2 parameter, showing the context help, the one for microstrain. This one was fixed at 0 in the previous refinement. As we can see in the results file here, B1 was refined. We see the results of the refinement, but we don't see K2, so it was not refined. So for that reason, it doesn't appear in the results file. So we can refine K2 and see if the fit improves. So what I do, let's go back to the previous state. That was our previous refinement. So what I want to try now is refine K2 for microstrain and maybe increase the texture model to a spherical harmonics of the 6th order. Let's try this. That's all we change, and run the refinement again. And indeed, we see quite a bit of improvement. Chi-square was a bit more than 1.8 in the previous refinement. Now we are at 1.65. So in fact, we do see the intensity mismatch is more or less resolved here. Not perfectly, but it's quite a bit closer to the measured data. What's going on here? I think there might be another phase hidden in here. Maybe this one too. We can check that in a minute. I'm not sure if there is something to improve here. So let's check if there is another phase. And if we remember the search match module, the list is cleared because I closed the window. We could just run it again, even though we already have a configured project. So it will immediately do a residual search, because it will already be using these two phases as pinned phases, and just search if anything matches the residual signal. But I want to speed it up so it doesn't take too much time. I will limit it to the pure calcium phosphates and even exclude the hydrogen phosphates and the hydrates. So this is a fairly strong restriction, and I will run it again. Okay, we already saw this phase before. It suggested it as a match in the first run. And now that we see a little bit more what's going on, actually this is exactly the phase we are looking for. So it's in the left side of this beta TCP peak, and here overlapping the K alpha 2 signal of the hydroxyapatite peak. So now that we have a pretty good fit of the main phases, we can actually see that there is another residual signal of this beta CPP. So we can select it here as by clicking on it. This phase will be selected in the reference structure list, and we go to the Add Remove Phase dialog. It will be pre-selected here because we selected it here, and we immediately click OK. And as we can see in our refinement control file, now we have 3 phases. Beta CPP was added, and the calculation of phase quantity was adapted. Now it will also consider the beta CPP phase. So now repeat the refinement and see if this part is fitting better now. And now we are getting pretty close. This part of the diffraction pattern looks really good now. We only see some random noise, no systematic differences anymore. Basically only these peaks here. We have some issues here, but the refinement gets very close. And now if we look at the chi-square value, it's now at 1.2. And we reached the blue range, getting closer to a value of 1, and maybe we can get it further down even more than that. If we look at the phase quantities, we now have 19.6% hydroxyapatite, 75.7% beta TCP, and the CPP, even though the signal was very weak, we had difficulties finding it. It's almost 5%. So it's a substantial amount. Now we have to fix the beta TCP structure. Is still not good enough. And we can maybe try to release some more parameters. For example, we could try anisotropic refinement, even though I said it doesn't make much sense in a high temperature phase. It's not impossible that the crystals are anisotropic. It could still be a little bit elongated, so we can try. It's a high quality data set. I don't think we will be over refining it by releasing this anisotropic size refinement. But it did not really improve chi-square a lot, so it's now it was 1.23, now it's 1.21, so that's not really a big improvement. Maybe the last thing we could try is increasing texture model once again, but it's getting very high now, so maybe it's too much. Yeah, again, we are only seeing very incremental improvements now. The next thing I would try to improve is I would check if some of the calcium is actually replaced with magnesium, which is a very common substitution, but I will not cover this in this project, in this tutorial. This is the topic of one of the more advanced tutorials. So maybe at this point we can see a chi-square value of 1.2. We are deep in the blue range now, getting close to 1. The difference curve looks pretty good. This, if we manage to fix these intensity mismatches here of the beta TCP peaks, it will not change the quantification very much. So the rest of the diffraction pattern is very well refined. So at this point, for a first tutorial, I think we can consider this a pretty good refinement, and we can continue and see what we can do now to export, for example, the refinement results. I briefly mentioned before that after the first refinement, another text file opened up here. It's got the extension LST, I call it the list file, and it's a text file with all the refinement results. Basically, the tables we see down here for the statistics, the global goals, so the quantities, and the phase-specific local goals, is just a summary of this file. So we see information on the BGMN version, the time and date of the refinement, how many iterations, and then the statistics, so the R values shown here. Profex also calculates the chi-square and the goodness of fit, and it extracts the background coefficients from somewhere else, but the RWP and the RX value are the ones shown here, and there are some more R values. The formula for how these are calculated are given in the BGMN user manual. And this is another BGMN specific goodness of fit value here. It's all described in the BGMN, not in the Profex, but in the BGMN user manual. And then we see the phase quantities. These are the same numbers we see down here with estimated standard deviations. And EPS2 is the parameter. We can actually use the context help. So it was refined. It's one of these displacement parameters that is refined in the control file, not in the structure file. So we are not in the beta TCP structure file, but in the refinement control file now. So I click F1. And now the context help says EPS2 is a specimen out of axis shift of the pattern sample displacement error. And if we go to the diffraction pattern, now we have this EPS2 value up here in this box, sample height displacement. That's the refined shift of the pattern. And if we reset it to 0, if we toggle between the refined value, actually the shift is so small we cannot even see a lot. So maybe now, yeah. So there's a tiny amount of shift due to a sample height displacement. That's the result of this EPS2 value that was refined in the control file, and the refined value is given in the list file right here. And then we see phase-specific results. In the BGMN terminology, they are called local parameters and goals. It summarizes again the space group information, the number, and the Hermann-Mogin symbol. It calculates the density based on the structural information. That's a value in grams per centimeters cubed. And a phase-specific R value, the A and C cell parameters, the crystallite size in nanometers in 2 different directions, along the C-axis and along the A-axis. So if this was a needle-shaped crystal, The C-axis would be much longer than the A-axis in case of hydroxyapatite. But here we can see it's almost the same value, so it's a pretty spherical crystal shape. And then we used the texture model spherical harmonics of the 4th order. We used anisotropic refinement of the crystallite size with a certain mean value and variation. And we did not refine any atomic sites, any coordinates or site occupancy factors yet. And the same for the beta TCP phase. All the summary up here, the refined unit cell, microstrain, crystallite size peak broadening, and all the elements, the atomic sites were fixed. And for beta CPP, the 3rd phase, we found it's the same. So this is the way BGMN summarizes the results. And here we get another summary just for a quick overview to keep an eye on the statistics and on the phase quantities summarized by Profex. And now we can export these results in various forms. The results menu shows which parameters we can export. The global parameters are basically phase quantities. So if we have a large number of refined projects, maybe from a batch refinement, we can export all these global parameters and also all the phase quantities to a single comma-separated table file. Now in this case, we only have one project. It will ask which projects we want to export to the same file. And if there were multiple, we could just check all and click OK and give a name. CSV, comma separate values. And now we can open a file manager. In the locations menu, we can go to the location of the current project. So this is our refinement project, the one we downloaded and extracted. Here's the raw data file we downloaded from the website. And now we should have the file here, global results. We can open it in Excel, for example, or LibreOffice. I don't have any Office suite installed here, so I will just open it in a text editor, and we can see semicolon separated values, the path and the file name, the sample ID, and then all these parameters. So the quantities with the value and the estimated standard deviation. And if we open this in a spreadsheet program like Excel, it's very easy to sort and process these values. We can very easily calculate mean values and standard deviations and do statistics on if we performed multiple measurements of the same sample. So this is very convenient for processing of the refined data. If we export the local parameters, we could do the same with the parameters listed here. So with the refined chemical composition, with the A and C parameters, so all the unit cell axes, of course also angles and B axis if they were refined. So exactly the same, we could export them to CSV files. The chemical composition, this is something we should look at now that the refinement is complete. We can open this window for the chemical composition again. And I will enlarge it a little bit. So now from the refined composition, the phase quantities and the chemical composition of the three phases, Profex computes the chemical composition of the sample. Of course, this is not as good as a chemical analysis like an XRF or an ICP, analysis, but it's helpful to see if we get close to a chemical analysis. So if this is close to something we obtained by XRF, it's a confirmation that our refinement was good. If there's major differences, if we refined a lot more calcium, for example, than we would find in an XRF, we know that we have to fix the refinement, that there's something wrong. Maybe we have the wrong phases, or maybe we did not find all the phases, or maybe they are contaminated, there are substitutions we did not find. So this is just a very useful tool to back up our refinement with some chemical information. And we can also export this to a CSV file exactly the same as with the previous two export functions for further processing in Excel or some other statistics program. The last export function is we can use now. The others are for different functions we have not yet discussed. The last one is the refinement report. We can generate a report. And this is a HTML file, so like a website, and it will open in a web browser. And it's just a summary of the refinement. It shows some sample information, statistics, the quantities, and the diffraction pattern. And we can print this from a browser, for example, to a PDF file. And the layout, the logos and the colors, and also the information. So which information is shown in the report, and all this can be customized, but we will discuss this in a different tutorial. So this HTML report is automatically saved in the project directory. You can open it anytime from somewhere here, the HTML file here. If you want to generate this report by default after every refinement, you can activate it in the preferences. In the backend configuration, create report after refinement. So it will always be generated, and you will always find this HTML file in your project directory after a completed refinement. We can also export the graph. So this diffraction pattern with all the information, the HKL lines, all the phase contribution scans. So for the individual phase patterns, we have different possibilities. For example, if you just click or press Ctrl+C for copy, a pixel, so like a screenshot, will be copied to the clipboard, and you can paste it to some other program like PowerPoint or Word. It's a pixel image. We can customize here in graphs, print and export the size, the resolution of this image. It's not very high by default, and the background can be transparent or filled with the background color, which is white here, or could be black in dark mode. So this can be customized to a higher resolution if you prefer that. A better option to export this graph is to use scalable vector graphics. We can go to Save As and export. So maybe I should start. If we click Save As on a text file, so for example on this refinement control file. I can only save it in text format. So I can name it test.txt. It will just be a text file, but this is the only option I have to save this file under a new name as a text file. But if I choose Save As on the graph, I have a variety of output formats available. I can save it in a text format as a list of values, X and Y values, for import in some other software, for example in Excel or Origin or any other plotting program. I can also do the same with the HKL information up here. And I have a number of different output formats for GNUplot, for different other Rietveld programs like FullProf and Jesus, some exotic formats. I can also again save it as a pixel image. It will be using the same size and resolution we set up before. And the most important one is the scalable vector graphics. And I will show you why. So we can choose this format and call it one tutorial SVG, scalable vector graphics. And this is a very modern and powerful format because it contains all this data as vector drawings. So here we have our SVG file, and I can open it with a web browser, for example. All web browsers are capable of displaying SVG files. And as you can see, it's a pretty good representation of the plot in Profex. It uses the same colors, the same positions for the HKL lines, the same legend. And I can print it from here, for example, to PDF or just display it in a browser. But the reason why SVG is so convenient is it still contains all the data as in vector format, and I can open it with any vector drawing program, for example Adobe Illustrator or the free version Inkscape, which is open source and quite powerful. And if I open the file here, it's all grouped, but I can ungroup everything, and now I can still change the text. It's not a pixel image. I can edit, for example, if I don't like the way the letter theta is written here. I can edit the text. It's all vector. I can also change line width and line colors. I can remove the legend. So I have full access to all these elements. So I can really tweak this. I can remove this. I can tweak this graph until it looks just the way I want it to look and use it for a publication. So this is a quite unique feature. SVG is a very convenient format to create high quality graphs for publications. So I guess this is it for this tutorial for the basic steps, first steps and the first refinement. I hope you enjoyed it, you found it helpful, and if you like this video, please give it a thumbs up and subscribe to the channel, and I will see you soon.